In the previous video, we discussed block diagram of digital computers. Welcome to Module 1, Unit 3. This unit introduces you to the numbering system. At the end of this unit, you should be able to define numbering system, state at least two importance of numbering system, and convert from one numbering system to another. The basic unit of data in a digital computer is a binary digit, also known as bits. A bit consists of 0 or 1. In order to store numbers larger than 1, bits are combined into larger units. The numbering system that is being taught in school is called decimal or base 10. This numbering system is called decimal because it has 10 digits and the numbers is from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Any values up to 9 can be easily referenced in this system by a single number. Computers use switches that can either be on, 1, or off, 0. Therefore, its major operations is in binary, also known as base 2 numbering system. Types of numbering system. There are 4 major types of numbering system. These are binary, decimal, octa, and hexadecimal. Kindly check your courseware for a tabular representation of this numbering system. Conversions in numbering system. Programmers most work with base 2, binary, base 8, octa, base 10, decimal, and base 16, hexadecimal. Base 8 and 10 are often used because they are easily translated quickly to and from base 2 and are often easier for humans to work with than base 2. Before teaching assembly language, it is always essential to know how to convert from one base to another base. This unit explains how to convert from any arbitrary numbers to base 10 and base 10 to other bases. Arbitrary numbers to base 10 conversion. Converting from an arbitrary base n, where n denotes the base number, to base 10 simply involves multiplying each digit in base n by base n with a superscript of the significant number and summing all of the results. For example, converting from base 5 to base 10 is performed as follows. 421 in base 5 to base 10. Now you write 421 base 5. You will now use the 4 multiplied by the base number plus the next number multiplied by the base number, then followed by the last number multiplied by the base number. Then the next thing is to start writing from 0, 1, and 2. And this will now be summed up. Now if you say 4 times 25, you will have 100 plus 2 times 5, which is going to give you 10, plus 1 times 1, which is going to give you 1. So if you sum all these together, you will have 111 in base 10. In other words, if you are converting from base 5 to base 10, you write the number, you pick each of the numbers that needs to be converted and multiply it by the base number. At the end of the day, everything will be summed up and you are going to have 111 in base 10. Now, another type of conversion is from decimal to binary. Decimal to binary conversion is by a process of repeated division of the decimal number by 2 until the quotient is 0 and keeping the remainder at each division as the equivalent binary. An example of converting from decimal to binary is given below. Now convert 42 in base 10 to base 2, which is binary. Now we'll do a repeated division of the number with 2, which is the base number. So 2 in 42, you have 21 remainder 0. 2 in 21 will give you 10 remainder 1, while 2 in 10 will give you 5 remainder 0. 2 in 5 will give you 2 remainder 1, while 2 in 2 will give you 1 remainder 0. Then we'll do 2 in 1, which is going to give us 0 remainder 1. 1 is the last number there. Now the answer will be written from bottom up. So if you write it from bottom up, you have 1 0 1 is 0 1 0 in base 2. This is the answer for converting 42 in base 10 to binary. Now converting from decimal to hexadecimal, it is very compact using base 16, meaning that the number of digits used to represent a given number is usually fewer than in binary or denary. Remember that the microprocessor only works in binary. All the conversions between hexadecimal and binary are carried out in other circuits. Decimal to hexadecimal conversion is by a process of repeated division of the decimal number by 16 until the quotient is 0, and keeping the remainder at each division as equivalent binary. Now convert 759 in base 10 to hexadecimal. 759 in base 10 to base 16. Now the conversion is you keep dividing the decimal number, which is 759, by 16, which is the base number. So if you divide 759 by 16, you will have 47 remainder 7. Again, you divide 47 by 16, which is going to give you 2 remainder 15. Again, you also divide the 15 by 16, and it's going to give you 0 remainder 2. So if you want to write the answer again, you write the answer from bottom up. So at the end of the day, we are going to have 2. 15 in hexadecimal, any number from 11 to 15 is being represented as letters in hexadecimal. So our 15 here now is going to be represented by F. So we are going to have 2F7 base 16. In other words, instead of writing 15 in hexadecimal, it will be represented by F. With this, we have come to the end of this module. See you in the next module, where we'll be discussing registers.